sit right here, is that okay? To lecture, maybe closer to the microphone here. So let's jam with it here. So this is 4.6, and the last sort of thing of, just like chapter 1, remember it had all the, what is fair, right? So you're going to have sort of something like that here too. And the rules that make it, and then also something called the paradoxes here. So let's go for it here. So all of yours, let you guys read it here. Here are the 3 facts about the apportionment methods discussed. So except for Hamilton's methods, all of the methods discussed violate the quota rule. Interesting, okay. Wonder what the quota rule is, just a little bit here. Hamilton's method can produce apportionment paradoxes given results that are unexpected or seen to violate common sense. Did you guys think that way as well? Just because a fractional part is higher, they get the next piece here. And at least according to the author, he says, look, that kind of is not fair because just because you were closer to the next number, bless you, it almost allows the higher states to still have more control, as opposed to helping the lower states to have more pieces in it here. So it is impossible for an apportionment method to satisfy both the quotient rule and not produce an apportionment paradox. Okay, I'll let that be. Let's look at some numbers here. So quotient rule says this: so that every state should be apportioned either its lower quota or its upper quota. That kind of makes sense, right? If it's a quota rule, it's either going to be this one or this one. The basic idea behind the quota rule is that the standard quota is the true measure of a fair apportionment. So, fair apportionment method, therefore, should not differ from the standard quota by more than 1 seat. Okay, let's see. Standard quota says like it's at a 138.72. That's reasonable, really, for it to have either 139 or 138. We good there? But it never should exceed those two. So if it rounds up or rounds down, that's where it should stay. That's the quota rule. Okay, so 2 types of violations, of course. An upper apportionment more than its upper quota. We say that violates the upper quota. Again, 138.72, it gets 140 seats. Okay, the lower quota violations. It's less than L seats. It violates the lower quota. For example, lower quota is 138.72, but then it only gets 137. So it's a little too far lower than even dividing by. Okay, are we good there? So let's kind of think through these little pieces here. So Hamilton's method satisfies the quota rule. It starts by rounding all the quotas down, correct? So you're at least going to get the lower quota for sure, right? And then afterwards it adds an extra seat, so then you're going to get, some states are actually going to get their upper quota, and that's it. There's no more seats available. We good? So it stays within that little range all the time. The Jefferson method is going to violate the upper quota rule because everybody's given the upper quota already, right? And then if you go even higher with more seats to give, then you're going to violate that one. Adams method, because of the lower quota, Adams method is if you want to look back at your notes here, for Adams method, Parador's Congress, Adams method would be 137 seats, even though the standard quota, if you were going to divide it by the number of seats, you should have had 138.72. And let me go back real quick. Let's go back in our notes for that one, just to make sure. So I'm going to go look at all slides. Let's go back to Adams method, and then we'll jump find a suitable divisor, right? and then keep on going. Let's see, each state is a portion of its upper quota. And then you keep on going. Now let's look at some numbers here. Oh, sorry, not Adams' method. So Adams' method by John Quincy Adams here. Everybody gets their upper limit. And so if you guys, you almost have to calculate the initial one as opposed to the modified one, right? So the initial number of seats, you should have been dividing by 50,500. That's your original divisor. And if you did that one, then this little seat right here, it would have been 138 point. I'm going to get it here, 72. That was the original, if you divided everything by 50,500, right? But for Adams' method, what we do is we keep on making the denominator bigger and bigger and bigger, right? So from the original one, it should only went to 139 or 138, but eventually with Adams' method, it winds up with a 137 only. Okay, are we good there? It violates that rule. So let me jump back down to where we're at. Okay, are we good with that one? Webster's method, Huntington method, though rare, you can have either upper or lower violations. So how do we do this? We take the number of seats, we go back to our original divisor. We take the number of seats, right? We get the population, we divide it, and that's going to be our first sort of numbers. And that's going to be the standard. So you either go up or one down. Anything that goes away from it is going to trigger something. But Hamilton method always does it because that's what you're doing. Jefferson method could violate the upper quota. Adams could violate the lower quota. Webster's method, Huntington Hill method could violate either or, depending on the number. All right, and then we have these. We have something called paradoxes. So it's when a state gets a portion fewer seats simply by virtue of the fact that the total number of seats being apportioned has increased. So what happens here is you have a let's see. Hamilton's method. You have the lower quotas. So if you were to increase the number, once you get past that 0.5, right, that means another state could get a lower amount. Does that make sense? See, I think that let me go back. Let me just make sure that's true. Let me go back to the Hamiltonian method here just to make sure it makes sense for us. Let's look at some numbers here. And let's see what this says here. It says that the Alabama paradox is just the fact that you have think if I agree with that here. So for the Hamiltonian method, you divide, right, by how many you have. Total divided by how many seats. And then everybody gets a lower quota, correct? So population, let's say we increase the seats to 255. And so now your decimal is going to be a little bit lower. So yeah, you can, especially this one right here. If the number of seats have decreased, right, your denominator just became a little bit bigger. So this can go underneath 3, and now you're stuck at 2. We're good just by increasing the number of seats. Everybody else is going to get more, but because your divisor became a little bit bigger, now state C just got now 2 votes only. It may get its third back because it's going to be close to, like, it's going to be 2.8-ish, right? But it is going to lose a seat just because of just increasing the seats. Okay, does that make sense to you guys? Okay, population paradox occurs when a state gets a portion fewer seats simply by virtue of the fact that its population has increased. The following example illustrates population paradox. That one we have not seen before, so let's take a look at that here. Oh boy. We are in the Intergalactic Federation. Sounds like Star Wars here, or Star Trek at least. And so apportionment 25-25, here it is, using the Hamiltonian method based upon the population in billions. There's 50 seats in this little Congress. So under the Hamiltonian method, here it is, all these different interesting pieces here. So let's see, we get this. That's the total population. All right, we divide by 50, each one of these here. So 150 divided by 50. Or divisor, whatever this is, right? Let me bring it up here. Okay, are we good there? Everybody receives their lower quota. Everybody good there so far? So everybody at least gets, everybody's at 48. We have 2 more that we can give. So that's going to go to 6.111 or 6.111. That gets another seat. And this guy gets another seat. All right, let's see what happens next. All right, and this is population in billions, right? So now let's see what happens here. 10 years of peace. We've got a little higher population. Now we increased it by 9 billion is the increase. So 909 divided by 50, which is right over here. Now our divisor is 18.18. So as we do that, here's our divisors, here's our quotas, and we're missing 2 more still. And so we're going to increase here. No, the surplus. Let's see. This guy is definitely the surplus. And then this is 25, 29, 22, 28. Ooh, this one gets the increase. All right, we're good. Still at 50 though, right? So what happened here? So let's go back to this one here. So notice that, anybody want to say that? Elysium. That's kind of cool. Elysium and then beta. Elysium got the extra seat. Now just because of population growth, Elysium loses the seat. And the seat now goes to beta. Are we good? Just strictly because of population growth. And let's see. Notice that beta, where did the population growth increase? This is no fun. Totally no fun. Look at that. Beta has 78. Elysium has 295, right? Notice that beta did not increase population at all. It was actually this state that increased the population. But because of the population growth, they actually lost the seat. That's not cool. And so one more time real quick here. It was at 0.33. Sorry, 16.38. That's what gave it to us. And now it became 2.8, but this was at 2.9, so just barely a little bit above. Okay, we're good there. So populations, change in populations can make changes in apportionment only. Okay, let's go then. What we just talked about here, 17 to 16 seats. Okay, next one. Paradox occurs when a state apportionment is affected simply by virtue of the fact that a new state, together with its fair share of seats, has been added to the apportionment calculations. So here it is. We get a new situation happening here. So Metro Garbage Company has a contract to provide garbage collection and recycling service to 2 districts in the metropolitan North Town. Yay. And the much larger South Town. The company runs 100 garbage trucks, which are portioned under Hamilton's method according to the number of homes in the district. That makes sense. Quick calculation shows if you add them all up, divide by 100, you get 1,000. So 1,000 is your divisor. Are we good? So we have that. Southtown is 90, Northtown is 10, which kind of makes sense. If you guys, does that make sense? That it's about 9 times bigger. Is that right? I'm thinking like from 10 to 90. That's about 9 times bigger, right? All right. Now imagine Metro Garbage Company is now bidding new territory called Newtown, 5,250 homes. And so this one comes into play. Now the total is this. Right, but it already has, real quick here, it already has 5 new garbage trucks, so they're trying to compensate with the new garbage trucks as this town comes in. Of course, there's bigger. So you figure from here, it looks like about every 10,000 gets you 10 garbage trucks, right? But there, that's almost at 90,000. That gets you 90 garbage trucks. And so you got this new town coming in with 5,200, and it has 5, and the garbage truck company is going to buy 5 more. Should be even. And so here's where we're at. We get our answer. We get our divisor. It's this divided by 105 now. And what happened here? Let's go back from here. So Northtown got an extra one. Southtown lost. And so this one. So a new state comes in, and this got changed. We're good? It's no longer a 1090 split. It's a 1189 split. Okay, we're good there. So there's your different paradoxes. And a nice little chart you may want to use for a test sometime. Cool. Okay, so Hamiltonian does not do any violations. We just covered all this here. So yes, but it's subject to these little population issues. So it's kind of interesting. Look at that. If you don't violate the quotas, you're going to violate the paradoxes, right? If you violate the quotas, then you're not going to violate the paradoxes. Okay. And of course, there has to be something impossible, right? Just like in chapter 1. So here it is. Of the 5 methods, Webster's method and the Huntington-Hill method are in the most sense the best because while in theory they violate the quota rule, in practice that hardly ever happens. So here it is. Belinsky and Young's Impossibility Theorem states that any apportionment method that satisfies the quota rule can produce paradoxes. Any apportionment method that does not produce paradoxes violates the quota rule. You can't have both. We good? It's kind of like, can you have a fair election, right? That's the whole concept of fairness. All right, so therefore you're gonna violate one or the other. Okay, that's kind of how it boils down to. All right, let's jam with it here. So here it is. If the standard quota of state Y is 78.24, then which of the following apportionments to state Y is or are possible under Adams' method? Okay, so this one's a little bit tricky. You got to think back in your mind, right? What does Adams' method do? So we got what, 1, 2, I think, yeah, 2. So let's go back, not so much as not so much as trying to figure it out, because you can't. You don't even know the population. You don't know anything here, right? You just have a number, right? And you have which method you're using. So let's go back to here. And we are talking about Adams. Adams method, right? Adams method here. So you can have a lower quota violation with Adams rule. Okay. Let's go back to see what the lower quota is. All right, so any apportionment method to a state less than L seats that we say violates the lower quota rule. So we went from 138.72 and only got 137 seats. So it's going to fall below the low quota. So let's go fast forward here. So 78.28. So I'm going to say, let's see, so first things first, if I round up, the upper limit is going to be 79, are we good? The lower limit is going to be 78, and under Adams' rule, you could violate the lower limit, so then you also can have a 77 on your hands. So answer is A, are we good? Just based upon the rule that it could violate from time to time. Okay, everybody okay with that one? And of course I can ask you about the Jefferson method, right? I can ask you about any other of those as well at that point. Okay, I think everybody's done writing. Let's jam to this one here. Exercise 60, a long one here. Let's do this one here before time runs out here. This exercise refers to apportionment of nurses to wings in Plainsville Hospital, introduced in exercise 20. Great, so I put exercise 20 on the side over there. The answers to part A and B, so this answer and this answer in exercise 21 is an illustration of which paradox? So we have Alabama paradox, population paradox, and new state paradox, right? Those are the three. So suppose there are 20 nurses working at the hospital. Use Hamiltonian method to apportion the nurses on that based upon this. Suppose an additional nurse is hired at the hospital, bringing the total nurses to 21. Use Hamilton's method of apportionment for the nurses based upon table 4.3. Okay, we good there? I guess just a few people writing it down. Just want to make sure if you want to write it down. I figure it's also in your textbook if you need to stuff. All right, let's go with it here. So you guys talk to me here. Here's your different Okay, so paradox occurs when the state gets apportioned fewer seats, simply by virtue of the fact that the total number of seats being apportioned has increased. So is it the number of items being increased? Population? Did the population of the hospital go higher? Or was there a new hospital that was joined to the previous one that already had their own nurses, but then after the shuffle, these nurses got decreased? So that's kind of the three scenarios. Let's go backwards here real quick here. So did we join another hospital that had their own nurses? Now we're combining nurses together. And one wing gets less nurses. I don't think that's happening here, right? Are we getting was there more population of patients? No, that didn't happen, right? Okay, so then question is, are there more nurses? Yeah, there's one more nurse, huh? Right? So let's take a look at this right here. So A and B. So if you go back to, I think for you guys, let's see, 18. This is 60, right? So you may have to look at the answers for, because you guys answers to odd questions, right? Do you guys have answers to odd? Okay, so yours will be, since yours is, this is 60, yours will be 59, right? As far as homework is concerned. So you guys will ask a question about number 19 most likely. But let's take a look at it. So we have the A wing, the B wing, and the C wing. So under the first one, A wing was 12, B wing was 5, and the C wing was 3. That's the funny thing. Adding an extra nurse, what happened was the A wing got the extra nurse. Good there? The B wing also got an extra nurse. And then the C wing suffered, and that's not cool. It actually went down by 1. Just because of the way you would divide, and you get the divisor, just the way the math worked out afterwards. Okay, so answer is, yeah, the first one, the Alabama paradox. We good? The total number of nurses increased, and the C wing went down from 3 to 2. So it has to be both things. It has to be an increase of something, and also the seats have to go down, or the number that was originally apportioned has to go down. If it was just increased and then everything went up, and then one went up by 1, everything else remained the same, then it's fine. Okay, are we good there? Okay, that was 4.6.